Good evening, everyone. Am I audible to you?
Yes, yes.
Yes, good evening and a warm welcome to all the esteemed participants in the second day of our faculty development program on multivariate data analysis and structural equation modeling using SPSS, organized by Bharatiya Vidya Institute of Management Science, Kolkata, in association with SPSS and the Indian Economic Association. Today, our topic is multiple regression analysis, and for that purpose, we have very esteemed faculty member, Dr. Tathagata Bandyopadhyay. He is former professor and the dean faculty, Indian Institute of Management Science, Ahmedabad, and he is serving as the director of Dhirubhai Ambani Institute of Information and Communication Technology. Welcome you, sir, from Bharatiya Vidya Institute of Management Science in this FDP, and thanks to you for accepting our invitation. You can start now, sir. Thank you.
Thank you very much. Shudipto,
Yes, sir. Yes, sir. Tell me.
how many participants you got for this program?
We got for this program around 75 total. So few of joined and few are joining. So total 75 around.
Okay, that's a good number actually. I was thinking.
Yes, sir. Yes, sir.
So, but I know that I am disappointing you because you called me last night and asked me whether I will be using SPSS. I said no way it is possible because the concept of regression, if you have to understand, you need to have around 5-6 hours, and then the question of SPSS will come. So, but I think Gautam can do a little bit of SPSS, little bit of regression using SPSS. I had to talk with Gautam. Gautam will do that possibly in his session. But I will basically focus on the concept of regression. And I will start with simple linear regression, and then I will go to multiple linear regression. Okay. So some of you may be knowing simple linear and multiple linear regression both, but still I would like to tell you that I will explain the concepts using data. So I will not start with a theory and a model and something like that. I know that this is a program for people who are not from statistics background. So but they use statistics for their research. So considering that, because you would be interested to know that given a data set, how would you use regression analysis and what kind of inference or conclusions can be drawn by using regression analysis from data. And I can tell you that regression analysis is one of the most important tool for data analysis. Okay, so everyone who is using statistics for analyzing data, they need to understand the basics of regression analysis. Of course, SPSS will give you output, but in order to understand what you are getting and in the context of your data, what does it mean, you need to understand the basics of regression analysis. And that's what I will explain in this session. I'll try to explain in this session. So let's start with a data set. You see that, is it visible to you all, the data set and whatever I have written there?
Yes, sir. Yes, sir.
So you see that I started with a data set where there are two columns. The first column is showing the size in square feet of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 apartments. And the second column is showing the selling price of these apartments in US dollar. Okay. So you have data on the size of the apartment, which is the first column. And in the second column, you also know the price of the particular apartment. And suppose my interest is that I am going to sell my apartment and I would like to predict, given the size of my apartment, I would like to predict what kind of price I can get in the. So to solve that problem, what I did, I went to the local municipality office and I asked them, can you give me the size and selling prices of the apartments that have been sold in the last month? So they said, okay. So they gave me these 11 apartments were sold. The sizes of the apartments are like this, and the selling price is the second column. Okay. So for example, you see the first apartment, its size is 1404 square feet, and its selling price is $1,09,360. Okay. Similarly, if you look at the last one, the size is 2040 square feet, and selling price was $154,890. Okay, so these are the size and selling price data. So now, from this data, suppose my apartment, the size of that is 1500 square feet. Okay, so I need to predict that what kind of selling price I will get if I go to the market and sell my apartment. Okay, what is important here, you see that size is, we often called a variable. Okay, a variable means a quantitative character which takes different values. So size is a variable, and selling price is also a variable which takes different values. So I have two variables, okay? And let's say I am saying that, okay, size I will call independent variable, and selling price of an apartment I will say dependent variable. Why? Because I am saying it, keeping this in mind, that what is my problem? My problem is, given the size of an apartment, I need to predict the selling price of the apartment. So the value of the variable that is given to you, okay, that is independent variable. So your problem is to predict the value of a dependent variable given the value of an independent variable. So in this case, my problem is to predict the selling price given the size of the apartment. So size is an independent variable and selling price is the dependent variable. So now the question is, this is often called bivariate data. So your FDP's title is multivariate data analysis. So this is a kind of multivariate data analysis because you have data on two variables for every apartment. Okay, I will come to the discussion when I will have three variables for each apartment. So usually two or more variables if you have for each apartment or each individual, then we say that is a multivariate data, multiple variables data. Okay, for example, suppose my problem is to predict the height of a person given the person's weight, or the converse problem. Given the height of a person, my problem is to predict the weight. So then what I will collect? I will collect, say, data on 100 individuals. And what I will collect the data on their height as well as weight. So that means it's a bivariate data. Both height and weight I am considering these are the two variables. And if my problem is to predict the weight given the height, then height is the independent variable and weight is the dependent variable. And if my problem is the other way, that means given the weight, my problem is to predict the height, then weight is the independent variable and height is the dependent variable. But suppose I have to predict the food intake, okay, in terms of calories, say. Food intake in terms of calorie, on the average, what is the food intake of a person? I can get it from asking him, what did you eat in last 7 days, every day? I can get an average calorie intake for each individual. Then what I could think about, okay, if height and weight of a person is given, can I predict the calorie intake of that person? So then I have in a situation where I have 3 variables for each individual, height, weight, and calorie intake, and I want to predict the value of one of the variables given the values of the other 2 variables. That is kind of 3 variable situation. So whenever we are considering data for each individual or for each unit, in this case, unit is an apartment, and in the other case, what I described just now, it is the unit is an individual. When I observe data on more than 1 variables for each individual or unit, we say that we have a multivariate data. Okay, we have data on multiple variables for each individual or unit. Now, what is the essence of multivariate data? So some of the questions I already posed in the context of this particular example. So you see, the question 1 that I posed is, what kind of relationship is there between size and selling price? So my problem is to predict the selling price. And why I am using size to predict selling price? Because intuitively or from the domain knowledge, I know that size has some relationship with the selling price. For example, I know that if size increases, the selling price tends to increase. Why I'm saying tends to increase? Because what happens, suppose there are 10 apartments, all of these apartment size is 1,000 square feet. But the selling price of these 10 apartments won't be exactly equal. Even though their sizes are same, but their selling prices could be different. But on the other hand, if I consider 10 apartments whose sizes are equal to 1,000 square feet and 10 apartments whose sizes are equal to 1,200 square feet, then I would expect that the selling price of the 1,200 square feet apartments would be on the average more than the selling prices of the 1,000 square feet apartments. What does it mean? Suppose I have 10 apartment selling prices, all of which are 1,000 square feet, and they are different. So I can find the average of that. That means average selling price of an apartment whose size is 1,000 square feet. Similarly, I have 10 apartments selling price whose size is 1,200 square feet. And I can again calculate the average of these 10 selling prices of the apartments whose sizes are 1,200 square feet. So what I'm saying that on the average, you will see that an apartment of 1,200 square feet selling price would be more than the average price of a 1,000 square feet apartment. So that means that one particular 1,000 square feet apartment selling price would be more than one particular apartment selling price whose size is 1,200 square feet. Individually, I cannot say that always it will increase because it depends on location, its age, the builder. There are so many other factors that are responsible for selling price. So we are considering only one, size. Of course, that is one of the key factors which influence the price, selling price. But what I'm saying, suppose you have an apartment of 1,000 square feet, which is built by a very renowned builder. And suppose its price is 90 lakhs. You can get an apartment of 1,200 square feet in 70 lakhs if it is built by a less known builder. So that means I cannot always say that as the size increases, the selling price will increase. What I can say that on the average, that means if you take 10 apartments of size 1,000 square feet and find their average, and 10 apartments of size 1,200 square feet and find their average, the average for 1,200 square feet would be more than average for 1,000 square feet. So this is the meaning of what I said, that that as the size increases, the selling price of the apartment tends to increase. Tends to increase means on the average price increases. So that is the question one. What kind of relationship is there between the size and the selling price? So that is the first question. Question two, estimate the relationship from the data. If you see that there is a relationship between the size and the selling price, can you find the relationship in using a mathematical formula? So that means if I give you, because the advantage of having a mathematical formula is this: if you give me the size, if I plug in the value of the size in the formula, then it will give me an estimate of the selling price. So can I develop a mathematical formula which gives you the relationship between size and selling price? And that relationship you will estimate from data, okay? Whatever data you have, from that data, you need to find an estimate of the relationship between the two variables, size and selling price. Third question, how strong is the relationship? That is, what is the strength of this relationship? Okay. So the strength of the relationship means that if the relationship is very strong, your prediction would be more accurate. And if the relationship is weak, then your prediction would be less accurate. So accuracy of the estimate depends on the relationship between the two variables. I'm giving you an example, what is meant by strong relationship and weak relationship. Suppose I am considering data on height and weight of 100 university students in US, okay? And I am getting the same data for 100 university students in India, okay? I picked up one university in US, suppose it is Michigan State University, and I got data from 100 university students. Of course, I am taking only Americans, 100 American students, their heights and weights. And again, I picked up a university in India, and I collected data on 100 students' heights and weights. And now you will see that the relationship between the height and weight for American students are much more stronger than the Indian students. The reason is that American students, they regularly go to gym and they maintain their physical structure. That means they are kind of, they're very, very sensitive about their health. And that's why they go to gym every day. And because of that, you will see there is a very strong relationship between height and weight. That means I am saying that if you consider 10 6-feet American students, you will find the variation of their weights is very small. For example, you will see that these 10 students' weight, actually the minimum and maximum, that difference could be only 5 kg. On the other hand, if you consider 10 students of, say, 6 feet in India university, then you will find that maximum and minimum may differ by 20 or 30 kgs. Because the Indian students are not that, what should I say, that they are careful about their health, and then they don't go to gym every day. And because of that, there could be a person who is very heavy and there could be a person who is very thin. So because of that, the variation would be too high. And that's why the relationship in case of Indian students is weak. And once the relationship is weak, then it's very difficult to predict. Given the, suppose the height of an individual, you can predict the weight, but that weight could be 150 kg as well as 60 kg. So that kind of variation is there. On the other hand, you may consider, when you are considering data on American students, you may find the weight varies between, say, 100 kg to 80 kg. So that means the strength of relationship in case of American students between heights and weight would be much more strong compared to Indian students. And if the relationship is stronger, then prediction would be more accurate. And that is why we want to know how strong is the relationship between the variables that we are considering, because our problem is to predict the value of one variable given the other. So I have already written there, you see, selling price is equal to dependent variable, often called response, and size is the explanatory variable, or often called predictor, or often called independent variable. And question 4 is, what is the predicted selling price of a house of size 1675 square feet? So you are given data on 11 apartments. The minimum size of the apartment is 1404 and the maximum is 2040. 1675 lies between 1633 and 1717. So from this data, what would be the predicted selling price of the apartment that you are going to sell, which is whose size is 1675 square feet. So already what I said, that if you know the relationship, if you can find a mathematical formula relating size with the selling price, then in that formula, you will just have to plug in 1675 for size, then you will get an estimate or predicted value of the selling price. Okay, I'm taking 1 minute from you. Okay, so just 1 minute. Okay. Okay, sorry. So now I think I can explain. I had been able to explain the problem. This is actually a regression problem that I need to solve. So basically what I'm saying in this case, there are two variables. One is size, the other is selling price. My problem is to predict the selling price given the size. And in this case, I will say size is an independent variable. Selling price is a dependent variable. So I have data on size and selling price of 11 apartments. And from that data, I would like to see, first of all, that what kind of relationship is there between size and selling price. Second, can I get an estimate of that relationship from the data? And third, how strong is the relationship? And fourth, given the relationship, what is the predicted selling price of a house of size 1675 square feet? Okay, so question 3 is important because, as I told you, that if the strength of the relationship is high, is more, then you would expect to get an accurate estimate. On the other hand, if the strength of the relationship is weak, then you would expect to get a rather poor estimate or predicted value of the selling price. So to do that, what I did, you see that I have shown you a picture. Okay, so what does this picture show? This picture shows on the horizontal axis, I have plotted the size. Okay, the size of the apartment, and along the vertical axis, we plotted the selling price of the apartment. So in that case, I have 11 such points. The x coordinate or the horizontal distance from the origin of that point is size, and the vertical distance from the horizontal line is y, which is the selling price. And I have just plotted these 11 points on this particular graph paper. And what you see, you can easily see that these points are not exactly on a line. Okay, it's not exactly on a line. But what does it show? It shows that as the selling price of the apartments increase, there is a tendency to increase, there is a tendency of selling price to increase. So it shows that as the size increases, there is a tendency of selling price to increase. If we have this kind of situation, we say that these two variables are positively correlated. Okay, positively correlated means if the value of one variable increases, there is a tendency of the other variable to increase. In such cases, we call there is a positive correlation between these two variables. Okay, and if I have a different situation, there could be a different situation where if the value of one variable increases, the value of the other variable tends to decrease, just the opposite. Okay, here you see that the points are upward moving. In the case, suppose in an example where the points are downward moving, okay, so in that case, I will say, okay, if the value of one variable increases, the other tends to decrease. That means there is a negative correlation between these two variables. So this kind of relationship is called correlation. Okay, correlation means two things. One is the relationship is something like this: if one increases, the other tends to increase, or the other tends to decrease. In the former case, we say positive correlation. In the latter case, we say negative correlation. And you see, there could be nonlinear relationship also. Nonlinear relationship, that means, okay, one more thing. So you see that what I'm saying, if the value of one variable increases, the other tends to increase. That means we have a linear relationship. We say we have a linear kind of relationship. Because in case of a line, you see that it doesn't change its direction. If one variable increases, the other tends to increase or other tends to decrease. So this kind of relationship we called linear relation. So correlation is a measure of the extent of linear relationship among the two variables. Okay? So this is very important to remember, that correlation is a measure of the extent of linear relationship between the two variables. It fails to measure the nonlinear relationship between the two variables. Sometimes the variables are related, not linearly. Maybe they have a nonlinear relationship. In that case, even if they are related, the correlation may be very small or maybe very poor, because correlation is not actually a measure which is used to capture nonlinear relationship. So I am talking about linear relationship between the two variables. That means linear relationship means if one increases, the other either tends to increase or tends to decrease. Okay. So now here we see that what we have shown in this particular picture, that we have shown the points, and the points are not on a line. Okay. So you see, I have drawn a line also. I will talk about that line later. So some points are above the line, some points are below the line. For example, the first point is below the line. Second, third, and fourth are above the line. Fifth and sixth are below the line. Seventh is on the line. Eighth is slightly below the line. Ninth is on the line. 10th is slightly above the line. And 11th is slightly below the line. So that means the points are not exactly on a line, but more or less I can see that they have a tendency to increase. Okay, can I zoom the graph? Okay, sure, why not? Can you see it now? Okay, so now you see that it shows that the first point is below the line, second point, third point are above the line, fourth point is slightly above the line, fifth and sixth are below the line, seventh is on the line, eighth is slightly below the line, ninth is again on the line, 10th is slightly above the line, 11th is slightly below the line. So how I got this line, I'm coming to that later. But suppose, what does it show? That I have drawn a line which is going through the middle of the cloud. So if I say that these dots have created a cloud, so I am drawing a line which is going through the middle of the cloud. It is drawn in such a way that some of the points are above the line, some of the points are below the line. Okay, so this shows that there is a kind of positive correlation. There is a positive correlation between the size and the selling price of the apartment. Okay, so this answers the question number one. Question number one was, what kind of relationship exists between these two variables, okay, X and Y? My answer is, it is a linear kind of relationship and positive linear relationship, because as the selling price increases, size increases, the selling price tends to increase. Okay, this is the answer to the first question. Now, I'm coming to the second one. Estimate the relationship from the data. Okay. So, estimate the relationship from the data. How can I estimate this relationship from the data? So, let's try to understand that. Okay. For that, let me do, I'll possibly draw a table. Okay. So, you see, now I'm saying, I will use some notation. Suppose I am saying this is size. Oh. This is size and this is selling price. Okay. So size, I have data 1404 and selling price is 109360. Next 1477 and selling price is 137980. And in this way, the last one is 2040 and selling price is 154890. Okay. So usually size, in this case, I said independent variable. I denote this by X and this is by Y. X is the independent variable, Y is the dependent variable. And I have 11 data points and we denote it by, suppose the first data point, this is, I say X1, Y1. X1, Y1 is the value of X and Y for the first data point. X2, Y2 is the value of X and Y for the second data point. And similarly, the last data point, I will say X11, Y11. This is the value of X and Y for the last data point. So what is X1? X1 is 1404. Y1 is 109360. What is X2? 1477. Y2 is 137980. And X11 is 2040. And Y11 is 154890. So this is how we write actually the data. So this is a data. So I have 11 observations on the variables X and Y. X is independent variable, Y is dependent variable. So now suppose I found that X and Y are linearly related. I observed, and this diagram is known as scatter plot. Scatter plot. So whenever you will get such data, and if you want to find out the relationship between the two variables, what kind of relationship exists between the two variables, the first thing that you need to do is to plot this picture, which is known as scatter plot. That is, on the horizontal axis, you plot the independent variable, and on the vertical axis, you plot the dependent variable, and you will get such a picture. And these are called scatter plot. And from the scatter plot, you can see what kind of relationship exists between the two variables. Okay. So in this case, it is positive and linear. So my conclusion from this picture, scatter plot implies positive linear relationship. Okay. So to answer question 1, I am using scatter plot. I'll go to further. I'll go about it in a minute when I will talk about it more in question 3. So for the time being, I will look at scatter plot, and it is a positive linear relationship. Now, how do I express linear relationship? So do you have any idea? For example, if I write y equal to say a plus bx, a and b are constants. A and b are constants. Okay. So if I plot this relationship, this is a linear relationship. Linear relationship between x and y. So if I want to plot this relationship, what is the meaning of A and what is the meaning of B? Let's try to understand that. So you see, suppose this is where I am plotting y equal to a plus bx. Okay. So now, if I think about this, now if I put x equal to 0, then what would be y? Can you tell me what would be y? Any one of you?
So the Y is the selling price.
No. If x equal to 0, it is a. So x equal to 0 means here. And suppose this is a. So y is equal to a. Okay. Now, suppose if x equal to 5, then what would be y? X equal to 5. This implies y equal to what? What happened? What would be y? If x equal to 5, what would be y? If y equal to a plus bx?
Sir, A plus 5B.
A plus 5b, exactly. A plus 5b. If x equal to 6, what would be y?
A plus 6B,
A
sir.
plus 6B.
A plus 6. So here is 5 and here is 6. Okay. And suppose at 5, suppose b is positive. Okay. Suppose b is positive. If b is positive, that means as you are increasing the value of x, it is increasing. So at x equals to 0, it was like that. Now at x equal to 5, suppose it has reached here, which is a, this vertical distance is a plus 5b. Now at 6, it has reached a plus 6b. So now if you think about this difference, what is this difference? What is this length? Height?
Difference is B.
Difference is b. So now you get an interpretation of a and b. So what is the meaning? That means a is the value of y at x equal to 0. And this a is often called intercept. This is called intercept. Actually, this will be a line like this. This, if you draw, you will get a line like this. And what is b? B is often called slope. What is meant by slope? By slope, we mean if you increase x by 1, what is the change of what is the change in y. If you increase x by 1, that means you increased x from 5 to 6, then what is the change in y? B. Take any value. For example, if you want to change x from 4 to 5, again, what is the change? It is B. If you make it 10 to 11, what is the change? It is B, and that is called slope. Okay? And if B is positive, that means you are getting an increasing kind of line. On the other hand, if B is negative, then you will get a line with a negative slope. Okay? So A is intercept and B is slope. So, and y equal to A plus bx is often called, represents a line. It represents a line. And where A represents the intercept of the line and B represents the slope of the line. And intercept means the value of y at x equal to 0. That is intercept. For example, if A is negative, then intercept would be, this is, I am assuming A positive. But suppose if A is negative, then intercept could be like this. Okay. So again, A could be positive, A could be negative, depending on that intercept could be positive, intercept could be negative. And B represents the slope of the line. That means if you increase x by 1 unit, then what would be the change in B? Change in y. Change in y is B. And if B is positive, that means it will increase by an amount B. And if B is negative, that means it will decrease by an amount B. So this is the meaning of a linear relationship. Okay. So now you see that here I have got a relationship which is not exactly linear. Not exactly linear. But I can say approximately linear. Approximately linear. So now the question is, if I have to measure that x and y are linearly related, but what is their strength of linear relationship? Then what I am using something called correlation coefficient. Correlation coefficient, often called Pearson's correlation coefficient. And this is a very interesting measure. This correlation coefficient is a very interesting measure. It takes value, correlation coefficient, and usually it is denoted by R, denoted by symbol R. So R varies between -1 to +1. And in the middle, it is taking value 0. And when R equal to +1, it means that X and Y are perfectly linearly related with a positive slope. And -1 means their relationship is perfect linear with a negative slope. With a negative slope. Okay. So in case of +1, if you find the correlation coefficient value is +1, that means that X and Y are related in a perfect linear fashion, but a positive slope. That means as X increases, Y increases. On the other hand, if the correlation is -1, that means again their relationship is perfect linear, but with a negative slope. Okay? And 0 means no correlation. No correlation. Okay. 0 means no correlation. You see, I am saying no correlation, but no correlation does not mean, as I told you, no correlation does not mean no relationship. Because correlation is a measure of linear relationship. Then I can say that there exists no linear relationship. That means it could be non-linear relationship, and because of that, the correlation could be 0, but still they could be related. Okay, so that is very important to remember. And suppose if the value is, say, here 0.8, suppose here 0.8 is very close to 1 compared to 0. It is far from 0, but very close to 1. So what does it mean? That the correlation, the strength of correlation is strong. It is very, very strong correlation, 0.8. On the other hand, if you get a correlation 0.2, then you will say the strength is weak. The strength of the correlation is weak. But of course, in both these cases, I would say the correlation is positive. That means as X increases, the Y tends to increase. That means as the independent variable increases, the dependent variable tends to increase. In case it is minus 0.8, again, it is a strong correlation, but in the negative direction. That means as independent variable increases, the dependent variable, the value of dependent variable tends to decrease, but the relationship is very strong. And similarly, if it is minus 0.2, that means there is a negative correlation, but the relationship is weak. Okay, so this is the way we interpret correlation. And here you see that here what we got the correlation is 0.85852075. That means approximately I can say the correlation between the selling price and size is 0.86. That means the selling and size they have very good correlation. The correlation is actually strong. I will say strong. And as the correlation is strong, that means using size, you can get good predicted value of the selling price. On the other hand, suppose if you calculate the correlation coefficient from this data, if you find it is instead of 0.86, it is 0.26, then the correlation is really bad. It's not. From size, you can get a prediction, but that prediction would be very inaccurate. Okay. So the correlation coefficient tells you that how strong is your relationship between X and Y. And that is the number question 3. How strong is the relationship? I am answering by computing the correlation coefficient. But how the correlation, or what is the definition of correlation coefficient? I am not getting into it because it's a little bit complicated. But correlation coefficient, what does it mean by it? And if you get a value, how do you interpret it? That I have already discussed. Okay. So in this particular case, the correlation coefficient is 0.86. That means it is quite strong. Now let's come back to the question number 2. Okay. That now what we observed, what we found, question number 1, answer of that is there is a positive correlation between the size and the selling price. Question number 3, we now answered the correlation coefficient between the two seems to be strong, which is 0.86. But you see below 0.86, I have written another number, which is approximately 0.74. What is this number? This number is nothing but square of the correlation, R square. This is nothing but, I will say, R square. Many times I will talk about it when I will consider 3 variables. What is the meaning of R square? So basically, in the case of two variables, you just compute R square, and R square actually tells you how good your data is for the prediction. I will come to the interpretation in the next sheet. Okay. So now let's consider the question 2, estimate the relationship from the data. You see that here we have already talked about the estimated relationship we have shown in this picture. The estimated relationship is y equal to 57.53x 57.53x plus 38928. 38928. So this is the estimated relationship. Estimated linear relationship from the data. So now I will explain how this estimate is obtained from the data. That is what I will explain now. It's very intuitive, the way it's just common sense for getting this. And you see, we have given the estimated relationship. This is a linear relationship, and this is often called the linear regression of y on x. This line is called linear regression of y on x. That means if you get a linear relationship where x is the independent variable and y is the dependent variable, the mathematical formula, I will say this is linear regression of y on x. That is of dependent variable y on the independent variable x. So this is the jargon that you will listen a lot of times in statistics. So basically this linear relationship is the linear regression, okay? And in this case, this is linear regression of y on x. Y is the dependent variable and x is the independent variable. So now I will focus on the question that estimate the relationship from the data, okay? So how to estimate the relationship from the data? Let's do one thing. Let's see if I can do that. Okay. So maybe I will use notes. Let's see. So let's see. So what we have already seen, that we have x, which is size, and we have y, which is selling price, and we have size and selling price of 11 apartments. So this is apartment 1, 2, 3 up to 11, okay? And size I said x, selling price I said y, okay? And I have different values of size. I said this is x1, the corresponding selling price is y1. This is x2, the corresponding selling price is y2. This is x3, the corresponding selling price is y3. This is x11, the corresponding selling price is y11. Okay. Now, we have found already that x and y are positively correlated. And correlation coefficient between x and y is around 0.86. That means strong correlation. Okay. And what does it mean? It means, this implies that one can approximately describe the relationship between x and y by a line, which is y is equal to a plus bx. Now the question is, yes, it shows that the relationship is linear. Now the question is, what is A and what is B? What are the values of A and B that I will choose? It's a linear relationship. That means here its relationship would be y equal to A plus bx. But I don't know the value of A and B. And if you change your value of A and B, you will get different lines. For example, if I have, this is x and this is y, if I have a line like this, if I have another line like this, if I have another line like this, if I have another line like this, for each of these line A and B are different because A is the intercept, B is the slope. So the question is how to choose A and B from this data. That means which values of A and B this data will give. In a sense that this line will give a very good approximate relationship between x and y. Okay, so this is the problem I am now trying to solve. So what is the idea? That I have been given a data, I looked at their relationship, they are linearly related, their correlation is very strong, so I know the relationship between them is linear. So that means their relationship is like y equal to a plus bx. But the question is, if I change the values of A and B, it will be different lines. So which line I should choose so that the relationship in my data, that is size and selling price, is best approximated. That's the idea. So to do that, what I will do this. You see, that suppose I am taking y equal to a plus bx is my line. So if my regression line is y equal to a plus bx, this is often called the regression line. Then if x equal to x1, then what would be the value on the basis of my regression line? For example, suppose actually the scatter plot is like this. Okay. And my line is like this. And suppose this point is x1, y1. So that means when x equal to x1, this is x-axis, and y equal to y1, I have this point. But this is my line, which I try to get, which will give me an approximate relationship between this, which is y equal to a plus bx. So when x equal to x1, from the line, my predicted value would be this. So the predicted value would be, this is the predicted value from the line. And that is, I will say, capital Y1 hat, which is equal to A plus BX1. So what I'm saying suppose I'm taking the linear regression as A plus BX. So then if x equal to x1, what would be the predicted value of y? I'm saying this is, I'm denoting by y1 hat. This is the predicted value of y at x equal to x1. When x equal to x1, what is the predicted value of y? A plus bx1 from the line. What is the actual value of y? It is y1. So you see that the predicted value y1 hat and the actual value y1, they are expected to be different. Okay? Because the points are scattered along the line. The points are not on the line. So whenever you are, suppose this is another x. Suppose this is x10. And in this x10, the predicted value is this y10 hat, which is a plus bx10. But what is the actual value? This is say x10, y10. So actual value is this. So that means the predicted value and actual value will not be same unless all the points are on a line. That means when correlation coefficient is equal to +1. But that's not the case. Our correlation coefficient +1 means then you don't have a statistical problem, because if you give me x, immediately I will say what is the value of y. There is an exact linear relationship between x and y. In most of the practical situations, you will find the correlation coefficient maybe 0.6, 0.7, 0.8, something like that. So that means the predicted value and the actual value will be different. So that means if I say y equal to a plus bx is my regression line, so my predicted value y1 hat would be equal to a plus bx1. Predicted value corresponding to x2 is a plus bx2. Predicted value corresponding to x3 is a plus bx3. And in this way, predicted value of the 11th observation is a plus bx11. So these are the predicted values. For different x. And what are the actual values? These are the actual values. Observed values of y. These are predicted values from regression line. Regression line is y equal to a plus bx. So now the question is, what is my objective? My objective is to determine a and b in such a way that the predicted value and the observed value are as close as possible. The predicted value and the observed value should be as close as possible, because you see that when the actual value is y1 and predicted value is y1 hat, then what is y1 minus y1 hat? What does it represent? Can you tell me? What is y1 minus y1 hat? What does it represent? Y1 is the observed value in the data corresponding to x1. And y1 hat is the predicted value of y from the regression line. So y1 minus y1 hat, what does it represent? Anyone? What is that? Error, exactly. Shayan said error. What kind of error is it? I will say prediction error. Okay, if I say this is the prediction error, am I right? Are you all with me? Okay.
Yes.
So this is prediction error. Prediction error. But how many prediction errors I can calculate here? How many prediction errors I can calculate? $11, exactly. So what are the other prediction errors? Y2 minus Y2 hat up to Y11 minus Y11 hat. And these prediction errors I am denoting by E1 because it is error, it is E1. This is E2 and this is E11. So E1, E2, E11 are the prediction errors. If I use the regression line as y equal to a plus bx. But what is my objective? My objective is to choose A and B in such a way that these 11 prediction errors in some sense are minimized. My objective is to minimize the prediction error so that I get accurate prediction. So the question is then, how should I choose my A and B so that these prediction errors are minimized? So one way to do that is this, which is called least squares principle. Least squares principle. Least squares principle does what? It says choose A and B such that the sum of squared prediction errors becomes minimum. That means E1 square plus E2 square plus E11 square is minimum for the chosen value of A and B. And this A and B are known as least squares estimates of A and B. So these estimates we got from data. Because how did we calculate this estimate? I calculated using data because in data I have some observed values and I calculated the predicted values and then I tried to minimize the sum of squared of prediction errors. For what values of A and B I will get the minimum value of sum of squared of prediction errors. And that principle is known as least squares principle. And the values of A and B which minimizes these are called the least squares estimate. Okay, so this is how once I get that estimate, I get the regression line. And that is what we have done here. You see that what we did, we created a regression line. Of course, I have done it using Excel. In Excel also, you can easily run the regression. So you see that the estimate of A and B that we got, A is 38,928 and B is 57.53. Now, how do I interpret the meaning of A and B? You see, what is the interpretation of A? What is the meaning of A? A is the intercept. And what is intercept? Can you tell me what is intercept? Remember? Intercept is the value of y when x is equal to 0. So from this regression line, what you can see? You can see that it tells you that the selling price of an apartment whose size is 0 is $38,928. Yes, Jaideep. So this tells you that when the size of an apartment is 0, the selling price is the predicted selling price would be $38,928. So you can tell me it doesn't make any sense. An apartment with size 0 means that the apartment doesn't exist. And your regression line is saying that the predicted value of an apartment with size equal to 0 is $38,928. It doesn't make any sense to me. I agree. But then what is the problem? It actually indicates, it tells you a serious problem about sometimes what we make this mistake. You see that our data are concentrated where X starts from 1400 something to 2000 something. Our data are concentrated between the values of X, 1400 something, which is size, to 2000 something. On the other hand, when we are talking about predicting the value of Y, something like this, here are my data. This is the minimum X, and this is the maximum X. So it is 1400 something, 1400 say 4, or 2040, something like that. But now you are extending this line. And your intercepts is here, 38,920 or something, okay? So what's the problem? Problem is your data is here. And you are estimating your relationship from this data. And you are trying to predict a value which is far away from your data. And that is called the danger of extrapolation. This is known as the danger of extrapolation. You are extrapolating the value of Y, but you are extrapolating not very close to your data. That means, you see, in this range, you don't have any data. So how do you know what would be the relationship between X and Y in this range? It could be something like this. It could be something like this. That means actually it is a nonlinear relationship here. So you don't know, you don't have any data, you don't have any idea about the relationship in this region. But you have data in this region, and based on that, you are extrapolating the value of Y for an X, which is far, far away from your data cloud. And that is called the danger of extrapolation. So you should not do that. Basically, your prediction would be good if you are inside your data range. If you are extrapolating, a slight extrapolation may be okay, but if you are far away from your data cloud, then it's dangerous. Okay, so that's why here the intercept actually doesn't make any sense. The reason is that intercept is giving you a value which is at X equal to 0, but your data are concentrated around 1400 something to 20 something. So it doesn't tell you anything which is sensible. On the other hand, if you look at the B, the estimate of B, so estimate of A is 38,928, but estimate of B is 57.53. What is the meaning of B? Do you remember? What is the meaning of B?
Slope.
Slope.
What?
The slope.
Slope exactly means what? Yes, slope.
So
What
it's increment rate or the decrease rate?
I have given you an explanation, giving an example, what exactly it is. I told you what is B. What I told you.
The change
Anyone?
of y with respect to x.
I gave you much more. Huh?
It's a change of y with respect to x.
No, that is okay, but I have given you much more specific amount of
That
change
is
in the.
that is if
Tell me, you are right track.
if x is increased by x is 1, what is the change in y?
Exactly. So if you increase x by 1 unit, then what would be the change in y? Okay. So what is x here? X is size. So 57.53 represents that if you change the size by, if you increase the size by 1 square foot, then the selling price will increase by $57.53 on the average. That is exactly the meaning. The meaning of this is if the size is increased by 1 square foot, then the increase in selling price is 57.53 US dollar on the average. This is exactly the precise statement of this. So that means if you increase the size by 1 square foot, what would be the price? What would be the increase in selling price? Would it be on the average 57.53? Why I am saying? Because for different apartments, the increase could be, some could be more than 57.53. Some could be, because some points would be above the line, some points would be below the line. So for some apartments, the increase could be above $57.53. And for some, it would be less than $57.53. So I am saying that if you increase the size by 1 square foot, on the average, the increase would be $57.53. This is the interpretation. Okay? Got it? Is it okay?
Yes, sir.
Got it. Okay.
Yes.
So now you see that I think that we discussed all these questions. Okay, now fourth question, what is the predicted selling price of a house of size 1675 square feet? What would be the predicted selling price?
So we will just put the value of x and we will get the answer.
Exactly, that's right. In this equation, put the value of x and you will get y. That is the predicted value. Is it okay?
Yes,
Okay.
sir.
Okay. So next we go to sheet 2. So because I need to discuss multiple linear regression, okay? So the earlier, when you have one independent variable, then it is called simple linear regression. But when you have more than one independent variable, we say it is multiple linear regression problem. So this problem, you see that I have just expanded my data set by including one more variable, which is age. Because I know the selling price is not only determined by the size of the apartment, also by the age of the apartment. That is, how old is this apartment? Okay. So that's why I have included another variable, which is age, and size was giving some information about the selling price. When I will include age, what should I expect? that it will give me more information about the selling price. So my estimate or predicted value would be much more accurate. Okay. So the question is, now we have again 4 questions. What kind of relationship is there between size and age and selling price? Okay. So what your domain knowledge is saying, intuitively what we saw, if size increases, the selling price tends to increase. And if age increases, the selling price, what? Would tend to decrease, okay? Older houses are cheaper, okay? So that means with size, it has a positive relationship, I would expect. With age, I would expect it has a negative relationship, okay? So estimate the relationship from the data. So how can I estimate the relationship from the data? Again, we'll do a similar kind of thing what we have done previously, exactly similar thing. So you see, I am saying size is the variable X, age is the variable Z. These are 2 independent variables. And selling price is Y. This is dependent variable. And I'm saying the relationship tells me that some kind of relationship like this would happen. Y equal to A plus BX plus CZ. This is a linear relationship or linear regression. Linear regression of Y now on 2 variables, X and Z. And these 2 independent variables, that is why it is called multiple linear regression. Because I am using multiple independent variables. Instead of 1 independent variable, I now have 2 independent variables. So now the question is, from this data, how can I calculate A, B, and C? That means for different value of A, B, and C, I will get different relationship. But I need to find the value of A, B, and C so that, again, the observed value and the predicted value are close to each other. Okay. So for that, again, I will calculate a table like that. For example, I will say X, Z, and Y. So here X1, Z1, Y1, X2, Z2, Y2, and I have X11, Z11, Y11. So these are the observed values. Now suppose I am assuming that the linear regression is Y equal to A plus BX plus CZ. So then if I have to predict from this line that my predicted value of Y at X equal to X1 and Z equal to Z1 is A plus BX1 CZ1. The predicted value of the second observation would be A plus BX2 plus CZ2. And for the last one, it would be Y11 hat equal to A plus BX11 plus CZ11. CZ11. And again, what I will do, I will compute the prediction errors. Which are E1 equal to actual value minus the predicted value, E2 equal to actual value minus the predicted value, and E11 equal to actual value minus the predicted value. And then again, we will find the value of A, B, and C such that find A, B, and C, find the values of A, B, and C such that sum of squared prediction errors is minimized. Okay. So this is again called least square estimates of ABC, least square estimates of A, B, and C. And here you see the least square estimates are this. So this is the estimate of A, this is the estimate of B, and this is the estimate of C. And you see, what does it say? You see that when my line is y equal to A plus bx plus c, z, then how would I interpret A? What is A? A is the value of y when x equal to and z equal to what? What are the values of x and z for which y equal to A?
0, sir.
0. So that means when x equal to 0, z equal to 0, then y equal to A. Okay. So that means when the size equal to 0, age equal to 0, what is the selling price? That is the kind. But we are getting it $28,000. Again, this nonsense or not sensible estimate I am getting because the prediction I am getting because the data cloud is far from the origin, from 0, 0. So intercept here doesn't make any sense. But let's go to the slope of size. There are two slopes here. B is the slope for size. B is often called the slope of size, and C is the slope of age. And what is the estimate of B? Estimate of B, you see, 69.21. 69.21. What does it mean? It means that if you consider houses with same age Z, same age, they have same age, but only you increase the size by 1, that is from X, you make it X plus 1, then the change in selling price would be B. So that means you are keeping the age constant. You are saying that if I am comparing the selling price of all the apartments which have same age, but then if I increase the size by 1 square foot, then the increase in selling price would be on the average $69.21. And what is the interpretation of C? If you keep the size constant, that means you are considering all apartments of size 1,000 square feet, but they have different ages. So if you in that case increase the age by 1 year, the selling price will decrease by $519.86 because it is coming with minus sign. Okay, so that is the interpretation that you are getting from the multiple linear regression. Those estimates are telling you this is the kind of situation you are having. Now, what is the predicted selling price of a 15-year-old house of size 1,675 square feet? What do you need to do? Your estimate, your regression line you got is this. Nah? Regression line is y equal to 28993.07 plus 69.21 times x, that is size, minus 519 0.86 times Z, which is the age. So you are asked to predict the selling price of a house whose age is 15 years. So here you need to put 15 and size is 1675 and you will get the predicted value of the selling price. Okay? Is it clear? Huh?
Yes, sir.
Okay.
Yes,
So
sir.
now, one more thing I will touch upon, but I will not get into too much details because this is something which needs more time. So you see that I have here talked about R square. I calculated R squared, which is 0.8764165. So R square is 0.876 means around 0.88, not 88, 0.88. So what does R square mean? The idea is this, you see, that the variation in the data is more than the variation in the values that you obtain by predicting the regression values. For example, I am telling you why. What is meant by that? For example, suppose this is actually the data. Okay. Okay. And this is your line, regression line. So for each X values, you are getting the predicted values. So the predicted values will be all on this line. So what is the maximum value of the predicted value? Here, this is max predicted value. And this is the minimum predicted value. And what is the maximum of actual values? Maximum of actual values is here. Max Y. And what is the minimum of Y values? It is here, minimum Y. So you see that the variation in the predicted values, if you look at maximum and minimum, is much less compared to the variation in the actual Y values. Okay. What I am saying, looking at this, you can say variation in the predicted values of Y is less than variation in the actual values of Y or observed values of Y. So if I denote BO is the variation in observed values, and BP as the variation in predicted values, then R square represents VP divided by VO. And this is here in this case approximately 0.88. So what does it mean? If you interpret, I will say that 88%, I will interpret it like this, 88% of the observed variation is explained by the regression, because the predicted value we obtained from regression. 88% of the observed values variation is explained by the regression. What could be the maximum value of VP? What could be the maximum value of VP? Can you tell me from your intuition, just from common sense, what could be the maximum value of VP?
1, sir.
VO. VP would be VO. That is observed variation and predicted variation in the predicted values would be equal. So VP is always less than VO, but the maximum value could be VO. And if that happens, then R square is 100%. That means all the variation in the data could be explained by regression. But on the other hand, suppose VP by VO is 0.001. What does it mean? Or 0.01, say. What does it mean? That 99% of the variation in the observed data could not be explained by the predicted values because it is only explaining 1%, which is 0.01. Isn't it? If R square is 0.01, it means that only 1% of the variation in the observed values is explained by the regression. That's a very, very poor kind of prediction you will get in this case. So more R square means your model is better. 100% means it is exactly, the relationship is exact. There is no error in the prediction. But usually you will get R square 70%, 80%. In certain contexts, that would be good. In certain areas, for example, if you are working in organizational behavior or finance, in finance, 1% or 2% R square is considered to be very good. In organizational behavior, 20 to 30% would be very good. In marketing, more than 90% you would expect. It depends on the domain also, because in certain domains, the data are more noisy, more difficult to predict. For example, in organizational behavior, you are predicting the behavior of human beings. Similarly, in finance, it's much more volatile. Basically, it's very difficult to predict what will happen. And that's why the R square is very small. On the other hand, in marketing, it is much more easy because if you know the price, if you know the promotion, if you know the brand, and from that you can actually predict the sales or whatever very well. And there R square would be very high. So R square is a measure of how good your model is. And high R square means your model is good. Low R square means the model is bad. Of course, it depends, as I said, on the domain. For example, in finance, 2% R square is very good. But in marketing, even 50% R square is very bad. Okay? So that you need to remember, and you need to, whatever your domain of knowledge, you know, if you go through the research papers in that particular domain, you will see what kind of R square people are getting. I think here I will stop. This is what I will stop, where I will stop. Any question now?
Yes, you can unmute yourself and ask any question.
Okay, so maybe I will. So
Is anyone from your end? Do you have any question? So you can unmute yourself and ask the question from today's topic.
I want to ask a question, sir.
Yes.
Good
Please
evening, sir.
stick
I am
to the
Ajay
today's
Kumar
topic,
Yadav from
Mr.
Bharatiya.
Jadhav.
Actually, I want to ask that in multiple regression analysis, how we define the partial regression coefficient and how significance testing in multiple regression analysis.
You know too much, so that's why I don't need to answer. For example, these B, the regression coefficient B and C, they are called partial regression coefficient. Okay, and I have not discussed the significance testing part. We can test whether these coefficients from the population, of course, not the observed value. From the observed value, we can test whether the population values have certain specific values or things like that. You can find confidence intervals, you can find prediction intervals, but that needs actually 20 sessions in regression analysis. You can consult any standard book, and any standard book talks about all this. But this is beyond the scope of what I have delivered today.
Okay, thank you.
It's a wonderful session, sir. Sir, Shans here.
Okay.
Sir, if possible, sir, can you explain, sir, a little bit about the concept of VIF?
Variance inflation factor.
Yes,
Again, to say that is very important for you, but for others. So basically, the idea is this, that when you have a multiple linear regression problem, sometimes what happens that for example, this I'm considering two variables X and Z. And if the correlation between X and Z becomes very high, that means if the independent variables are highly correlated, then that creates some kind of problems in the estimation as well as testing. And then what we need to do, we need to look at the variance inflation factor for each variable. And if the variance inflation factor is usually more than 10 for one variable, then you need to see that possibly that variable can be predicted by other variables very well. So you need to drop some of these variables, or you can use what is known as principal component analysis to create a kind of surrogate as a linear combination of other variables. And you can put that in your linear regression and you can carry on. So that's, of course, a very important problem, which is called multicollinearity in linear regression. But again, in one session, it's not possible to discuss all this.
Thank you, sir. Thank you so much.
No problem.
Sir,
Any
I
questions
just
from any
missed out.
participants?
Hello, sir. Hello, good evening, sir.
Yes, yes.
Hello, sir, could you please explain the steps to be followed under SPSS to calculate the regression?
I don't know. I told Shudipto that I will not talk about SPSS because SPSS is not my expertise. SPSS, you will know, you need to know the concept, then you can learn. Actually, Gautam will be taking sessions on SPSS and others are also taking sessions. They are using SPSS. But SPSS is a very powerful software for particularly the researchers in social science, I know. So, but I am not here to discuss SPSS. Okay.
So don't worry about it.
Okay, sir,
Dr.
thank
Gautam
you.
Bandyopadhyay will show you the steps in his session. Okay.
So, hello,
Yes.
Sudipto.
Yes, sir. Yes, sir.
So,
Please.
Tathagata, তুমি আমার প্রণাম নিও, you take my প্রণাম. Okay. What I'll tell, this is a wonderful session. So really, so definitely, Tathagata, I'll give some concept in SPSS in the last day.
Yes.
So I already had a talk with Sudipto that I start my class before half an hour. Okay. So half an hour, definitely I will show you some part of SPSS. Okay.
You start with a data set and just run the regression.
So I will show you on the last day.
Sure. I know. I talked to you, na?
Okay.
Called me. Are you talking
very,
about this? I said, no way.
So very nice, very nice.
So I have discussed all the thing with Gautam sir regarding this matter. So Gautam sir told me, no need to worry, I am there to show all the things.
Definitely.
In the last class. So just understand the concept because sir will give you a overall concept.
Sudipto, the last day, your right time is to start from 7. And if you start at 6:30, the first half an hour, I can show only.
Sure, sir. I will communicate to all the participants that we are going to start.
If they are interested. Okay.
No. Definitely they will be interested, sir. Don't worry about it.
Okay.
So I will definitely coordinate with all the participants that on that particular day, half an hour before, we will going to start the session. So any question from any participants? Otherwise, we are going to close today's session. And before closing, I would like to request Dr. Pauline Bandyopadhyay, Assistant Professor from BIMS. So for vote of thanks.
Sir, I just have one question. Mr. One part.
Yes, please continue. Please continue. Please continue. After that, we can go with Dr. Pauline.
If the value of R square is like maybe like 0.01 or 0.02, what does it represent? So I just missed out because there were like
Represents that, as I say, what is R square? R square is VP by VO.
Yes, sir.
It's VO is the variation in the observed data, and VP is the variation in the predicted values. Okay, so that means if VP by VO is 0.01, that means predicted values are coming from where? It is coming from regression. So that means 1% of the variation in the observed data can be explained by your regression, and that's very bad situation.
Thank you.
Okay.
Pauline ma'am, you can go ahead.
Okay. Good evening, everyone. I'm privileged to get this opportunity to deliver the vote of thanks today. I'm really honored to address you, sir, Professor Tathagata Bandyopadhyay. We are privileged to have you with us, who has taken out your time from your busy schedule and have delivered this expectedly informative session to us. And I also extend my heartfelt thanks to the convener for giving us this opportunity to listen to Professor Bandyopadhyay, which would have not been possible otherwise. So thank you very much, sir, for being with us all day long. And I also extend my thanks to Professor Gautam Bandyopadhyay for being here with us, who will also be there in future on the last day of the session. And he has been with us before too. So thank you so much, sir, Gautam sir. And in addition to that, all the participants without whose patient hearing, this session would have been incomplete. So I would extend my heartfelt gratitude to all the participants here who are present with us. And I'm sure all of us have benefited extensively throughout this session. So thank you, everyone.
Thank you, Pauline.
Thank you so much, sir.
And for all the participants, I'm sharing the feedback and attendance form. Please fill up the feedback form, because through that we are collecting the attendance. Yesterday, few of you have not filled up the form. So I am requesting all of you, please fill up the form. Okay, it is in the chat box. Thank you, sir. Thank you very much. We are going to close the session today. We hope you will be with us in future also in our various events. And it was not possible without Gautam sir. So I am also thankful to Gautam sir. And Tathagata sir, we are expecting you in our future events also. Please be there. It is our request. Thank you, sir. Thank you very much. Taking permission of our principal sir, we would like to close the today's session.
Sure.
Thank you, everyone. Good night. We'll meet you tomorrow, 7 o'clock. Okay, and please fill up the feedback form. Thank you.